All right, day 2 of applications of logarithms. Oops. So we're going to, at the end, come back to a little demonstration of logarithms and how they're used, which I hope you'll find kind of interesting. At least we will if we have time. Here's a couple of examples. You don't have this part on your handout, but you don't need it. A couple of examples of the logarithm scale. Now, this is the decibel scale, so loudness. And you've probably heard of decibels before. It's a bit of a strange scale in that there's an extra factor of 10 in it. So we're going to do an example on it. It's not something that you really need to worry about in terms of like being tested on it. But we're going to do an example. I don't know why it's this way, but a decibel level of 30 actually means the exponent is going to be 3. So we have to divide by 10 first. That's all. Like, it's not hard. We just have to know to do that. Okay. But it's the same thing. I imagine they do that so that you can have a decibel level of 85 as opposed to 8.5. I'm guessing maybe that's why they do it that way. I don't know for sure. Okay. So that's one example. And another one is pH. And the pH one, this little diagram or this little figure really shows what's going on, like shows it nicely what's going on with the log scale. So the different levels of pH are an indication of how many hydrogen ions are in it compared to water. So water is the sort of middle one, pure water, distilled water, has a pH of 7, and that's just a 1-to-1 ratio. Okay, so for example, black coffee has a pH of 5, but it's got 100 times more hydrogen ions in it. Okay, acid rain tomato juice 1,000 times more, but it's just a pH of 4. So it just makes the scale more user friendly, even though the multiplier is a lot bigger than it looks. And then the other direction, when you go higher pHs, you actually have fewer hydrogen ions. So the scale is kind of upside down. And that's why you'll notice if you look at the solutions in those that the exponent has a negative on it. Again, it's not something you have to worry about it, but that's why it's there. Okay. So there's a couple of examples of what the scale looks like. Let's take a look, at the first question. A normal conversation has a loudness of 60 decibels. A rock concert has a loudness that is 1,000,000 times more intense. Determine the decibels of a rock concert. Both of these were on the scale that we just looked at, so we could just look them up, but we're going to use math to figure this out. Okay, and there's a note here for decibels. We have to divide, then multiply by 10. Okay, so this is the kind where we're searching for one of the decibel levels, so we have to introduce x. So we're going to let x represent the decibels of a rock concert. So now for a conversation, is going to be 10 to the 60 divided by 10, so 10 to the 6. In fact, each one of these has a whole formula to it into how you actually calculate like the magnitude of an earthquake on the Richter scale or the loudness. Like there are other parts to the equation, but we're not doing the work with the equation. All we're doing is comparing different decibel levels. So we don't need the whole equation, but there are other parts. And in the decibel equation, there's a 10 in it, which just kind of accounts for this. Makes it kind of complicated more complicated when we're trying to, do these comparisons. But anyway, it's not a big deal. Okay, and then a rock concert. Is going to be 10 to the x. What's the little thing we have to remember when we're doing these? The only trick to these?
Put the bigger one on top.
Bigger one on top, and the bigger one is the rock concert, so it's 10, whoops, it's 10 to the x over 10 to the 6 equals 1,000,000. So this is 10 to the x minus 6 equals, turns out, 1,000,000 we can write in base 10. So we could do this with logarithms, but this one can actually be done with like the grade 11 method as well. No matter how you do it, you're going to end up with x minus 6 equals 6. Add 6 to both sides. X equals 12. To get the actual decibels on the scale, multiply by 10. Oh, 120. I didn't actually finish that. Rock concert is 120 decibels. Again, if you think about the difference between 60 to 120, it feels like that should be double, but it's not double. It's 1,000,000 times more intense, which makes sense. What would be double one person talking? Two people talking. Right? That would actually be double the intensity of sound. That's not what a rock concert sounds like. Two people talking at the same time. It's a little louder than that if you've never been to a rock concert. Any questions? All right. So we didn't do one quite like this, although they were in the practice. We did a half-life one, which is one that gives you the multiplier. So this one's a bit different. The number of bacteria on a surface is doubling every 10 minutes. So this is the doubling type, but it is the type where you're given the base. It's not a percentage increase or decrease type question. If there are currently 450 bacteria, how long until there are over 1,000,000? So I'm going to use B for bacteria. And remember, this is the strategy that I recommended, in particular if the question is a little bit tricky, or if you just like having sort of a structured way of doing things. We start by just picking the formula that we're going to use and writing it out. Yep? Okay. Notice this is something that happens kind of in grade 9 for younger students. Capital B is not the same as small b, and they'll interchange them. Like if I write a small b, they'll write a capital B in their notes. And, depending on the class, you kind of have to catch it and say like, no, you can't do that. Little b means little b, and we can see it in examples like this where we are allowed to use big B and little b at the same time. Okay, T over N. And then we're going to write out each of those and fill in the blanks that we know, figure out what it is we're looking for. And you don't have to do that, but it is a good way of structuring what you know and starting out the question kind of thing.
So if it's a percentage increase or decrease, it'll never be the one to like triple, double, and half-life?
Right. Right. So doubling is an increase of 100%. Right? It's not 1 plus 2. It would be 1 plus 1 to get the 2 that's going to go into the equation. Right? You take the amount that you have and you add that whole amount again. Now you've got double. So that's an increase of 100%. So B would be 1 plus 1. But we just think of it as a 2. That's the easier way of doing it. Somebody want to give me another one of these values? B naught in this case, but yep, the starting amount is B naught, so that's our 450. Yeah, Mara?
The N would be 10.
N is 10. So it's doubling every 10 minutes. That's the n. And some of the n's are a little hard to pick out. I've had some people asking, how do we know what the n is? And it is just true. Some of this is really about language. You just have to read the question carefully and understand what it's asking you to find and what numbers go to what parts. Yeah, and then B is a million. Good. Okay, let's sub in. Next step. Okay, we're dividing out the 450 from the right. Very good. You don't have to do this, but you probably normally would want to. Especially if your calculator can do it for you. Get your calculator to simplify that, just because it's less to write every time and less to type into your calculator when we put this in later. Little piece of advice here. Be careful of your zeros. I see a lot of people copying down the wrong number of zeros from the calculator or from the line above, right? So watch your number of zeros. Yep.
My calculator gives me this.
Interesting. It's in mixed. Oh, mine won't even give that. So if you hit the S to D button, it should give you different versions. Okay, we can fix that. Maybe it's a setting that I think we can fix it.
Mine has that as well, and if you click second function on the fraction button.
Second function fraction button, try that. Yeah, you're right. That does it on some, or shift on the fraction button. I don't know if it works the same on that one, but on some it does. Let's figure it out after. And 2 to the t over 10. Okay, now you can either take the log of both sides like we talked about yesterday, or you can rearrange this into logarithmic form. Again, you could do this, 8 equals 2 to the 3, which means 3 equals log, base stays the same, base 2 of 8. If you need to make a bit more sense of it, if you're finding you're getting confused about which part goes where. So t over 10, or you can write the t on the right side. Like, you don't have to write the t on the left side like I do it if it's more familiar doing it the other way. Log base 2 of 20,000 over 9. Move the 10 over. And if you have to change of base, you do that, and then into the calculator it goes. How about I'll do it this way. Whoops. 10 times log 20,000 divided by 9, close bracket, divided by log 2. 111.2. And we're in minutes. There we go. Yep.
Do you have a button on your calculator, like that just says, like, you just put it in, you still have to?
Of course not. No, you do not have to show that step. I'm only doing it for the people who have to do it that way. Okay, so 2 more, and they both have a little bit of a sort of twist to them. Something a little bit different from what we've seen so far. Not really harder, but it does identify how you have to read these carefully and make sure that you understand the numbers that you're being given and what you're being asked to find and understand what's happening in the question. Some application questions, word problems in math class. You don't even really need, like the word problem has nothing to do with the actual math. Sometimes that happens. But with these ones, you really do have to kind of understand what's going on. Arsenic 74 is used to locate brain tumors. Irrelevant to the question, but interesting. From a sample of 100 milligrams, only 6.25 milligrams would remain after 70 days. Determine the half-life of arsenic. So half-life, we often use M for mass. And we're using this version. Who wants to give me something?
I was just gonna ask, do we always have to do ever? Can we just keep them as A?
You can use A if you want. Evan?
T equals 70 days.
T equals 70. Interesting, because very good. We're usually solving for T, but in this one you're given T. Okay, something else?
M equals 6.25.
So M is the final amount, and that's 6.25. Good. B is a half, and it always is for half-lives. Good. Noor? A naught is?
100.
Or M naught is 100. Good. And N is what we're looking for. Determine the half-life of arsenic 74. Okay, so read these questions carefully, and are you solving for time or are you solving for N? Okay, now we can sub in. As long as you recognize that, these questions, oh, did I do that backwards? I did. Sorry, I was thinking about the end part. 6.25 equals 100, of course. As long as you recognize that, subbing in is easy. Solving isn't really harder. There's a little bit of a twist to it at the end, but it's not really harder or all that different, the rest of the steps from here. So you just got to recognize that this one's a little bit different from the ones that ask for T. Okay, so we're going to divide both sides by 100. And then that gives me 0.0625. Rearrange the log notation. Now here's where it's a bit different. I got to multiply the n to the other side and then divide the whole log part to the other side. And we end up with 70 over log 0.5, 0.0625 equals n. So nothing hard there, but you just have to be a little bit careful and realize that there's a bit of algebra and you're not just moving the 70 over and multiplying.
So could we divide both sides by 70 and then that's the inverse of?
Sure. However you want to think of it, you just have to get to this step and make sure that you've got the 70 and the log in the right order. Okay, again, there's a little trick here for those of you that are using the change of base formula. And I've been saying a lot of this lately, but you just have to figure out the way that works for you in your brain, your type of thinking. You could put it into your calculator just like this. As long as you've got brackets in the right place, you're dividing by the whole fraction. So that's important that you really use brackets appropriately. If you've got a fraction button, it makes it easier. Or if you use, and since we have done so much of this in the identities that we did in the last unit, you could do the fraction math and realize that if I'm dividing by a fraction, I flip and multiply, and this ends up being 70 log 0.5 over log 0.0625, like that. Okay?
Wait, why is there 70 there?
What do you mean? Where would it go? It's 70 over the log. So I use the change of base formula to do that. And then you would flip and multiply, so it would be 70 log 0.5.
But I don't understand how the 70 got on top. If
It's on
70
it's on top.
N, then wouldn't you isolate by multiplying by 1 over 70?
Multiply both sides by x. Divide both sides by 2. 10 stays on top.
But why doesn't 1 over 10 work? That's what I'm not understanding.
1 over 10?
Yeah.
I don't know what you mean.
Like, if you multiply both sides by 1 over 10, wouldn't that also...
It would do something with the 10, yeah? Do you mean like, so back to this step?
Yeah.
So if I multiply both sides by 1 over 10, I'd get 1 over x equals 2 over 10.
Oh.
Okay, so I punched that into my calculator. I got exactly 17.5. Therefore, the half-life of arsenic 74 is 17.5 days. Yeah. Did anybody's calculator give them something different when they did 6.25 divided by 100? Did anybody try that on their calculator? No? Really? It's got to be. 1 over 16. So it turns out that works perfectly. Oh boy, what is going on here? There we go. So, or you could have done 1 over 16 equals 1/2 to the 70 over n. And this is 1 over 2 to the 4 equals 1 over 2 to the 70 over n. And then what do we do? Just say the exponents are equal. And if you solve this, you get 17.5 again, n equals 70 over 4. And it's a little bit slicker, but don't expect that to happen on the test. That's a grade 11 type question where it works out nicely and you can solve it doing that. Grade 12, you're going to be using logs to solve these. So even if some of the ones from the practice work out that way, I mean, if you notice, it's nice to notice those things because that just means you're being observant, you're paying attention, and you're welcome to solve it that way, do whatever you want, but just recognize that, you know, you got to make sure you can do the log way. That's the important one for this course. Okay, any questions? So that was solving for half-life as opposed to, or solving for the time of the half-life as opposed to solving for time itself. Just a little bit different. This one's a little bit different too. Every time an object is put through a particular cleaning process, 60% of the bacteria on the object is killed. How many times must the process be repeated to have 98% of the bacteria killed? There's actually a couple of little things about this one that are different. So what kind is this? It's not increasing. Yeah, it's decreasing. This is the decay type, okay, because the amount of bacteria is getting smaller, is decreasing every time we put it through the process. So this is going to be, I'm going to use B again. One minus R to the T over N. What's R? This is not a trick.
0.6.
Yeah, 0.6 or 60%. 60 divided by 100, 0.6. T is what we're looking for. What's N?
It would just be 1.
Yep, it's 1. Because it's every one time the process happens. Yep. B and B naught. What are these?
Would B be 98?
Is B 98? So is that how much we have left at the end? Because that's what B is supposed to be.
2%.
Oh, 2%. So this is, again, a percentage one, right? So we don't know what the actual starting amount is. But if I said the starting amount was 100, wouldn't the final amount be 2? So this is, again, what I mean by you really have to read these carefully and think about the numbers involved. Think about what the question is saying. And understand, and even think to yourself, B is how much is left at the end. Is it 98% that's left at the end? No, that's how much that's been removed. So there's 2% left. So obviously 100 minus 98 gives you the 2. The other way that you could do it, as we did before, 1 for 100% and 0.02. And this just skips the first step that we're going to do. Whoops. Got them backwards again. 1 minus 0.6 to the t. Not so much in this course, I don't think, but in other courses, again, a mistake that people make is they put 60% in instead of 1 minus 60%. So again, just you got to think about what's the rate, but then what actually goes into the brackets. Divide both sides by 100. Okay. All right. Did you get 4.3? The process must be completed. Who wants to finish this sentence for me?
5 times.
5 times. So this is the other twist to this one. And there's a couple like this, I think, in the practice. 5 times. So 4.3 rounds down to 4. Why did we round up? Because we want to get to 98% or lower. And you can't do part of a process. You have to either do it or not do it. 4 isn't enough, so you round up to 5. This is the kind of question where you just always round up. And like I say, there's a couple like this, and you just have to identify when it's like that. It's often the ones that have a process where you either do it or you don't, where you just have to round up. Somebody was asking, some of the other ones, would you also have to round up to make sure, like there was one question where it says like more than 1 million, so why wouldn't you round up for that one as well? We're not as picky about those ones. We're just rounding normally for those kinds of questions. It's just the one that's like a process where you would always round up. Does that make sense? And again, you have to just read the question carefully to identify that it's that type. There's a few that are just a bit tricky. Okay, I'm going to show you some demonstrations of just some interesting things. And it's kind of just interesting from a interest perspective. Has anybody used Gapminder? Have you used this before? No? Anybody taking world issues this semester or next semester? Nobody? Oh. Usually there's at least someone. Or any kind of like geography course where you might be looking at studying data or something like that. Nobody in here? Fine, that's whatever. Anyway, that's fine. Gapminder is a really amazing tool. It's been around for a long time now. I remember when TED Talks were first happening, one of the first big ones was the guy who invented this software. And it was an awesome TED Talk, and he was just demonstrating it, and it was kind of mind-blowing. If you ever do take a course like that, it's a great way to get data because it's got tons of different options. Look at this under communication, economy, education, energy, environment, health, infrastructure, and when you click on them, there's all kinds. There's 3 there and 4 there and 3 there, and there's all different subcategories of information that you can get, and you can make your vertical axis whatever you want and your horizontal axis whatever you want. They're all in both axes, and it's got, this is back in 1800, so it's going to show us the change over time. And when I hit play, it's going to show up the years increasing. And it's also, you can't really see yet, but the dots are colored. So the colors correspond to sort of general geographic locations around the planet. It's not quite continental, but it's kind of close. And then you can do things like highlight certain countries and different things like that. Let's see what happens. This is income to life expectancy. So back in 1800, there wasn't a lot of data on this. So as the years go up, you're going to notice more countries appear as there are more countries that have data. Whoa, what was that? Close. World War I, right? Just about 1918. All of a sudden, across the planet, you see those numbers plummet. Interesting. I think this is speed. Maybe we'll speed it up a little bit. There we go. What's that big yellow dot? States probably. Yep. See, you hover over it and you get the specifics. It's really powerful software. Whoa, what was that? That red one. What do you think that red one is that's growing so big? China? Look, it's huge. China. All the way to 2018. Now, the graph doesn't show us that much. They were all kind of huddled to the side, and now they're just kind of all huddled to the top. It doesn't really show much. The reason why we're looking at this is because often in often in statistics, they will use a logarithmic scale because seeing a logarithmic or exponential relationship can be hard, but you can often see it's just easier to pick out a linear relationship, which is a straight line. But if I make the scale logarithmic, it will take an exponential relationship or a logarithmic relationship and make it look linear. So doesn't that kind of look, what's the relationship that this kind of looks like a straight line, wouldn't you say? There's a bunch up here and a bunch down here, but none really here or here. So what's the relationship here? If it's income across the bottom and life expectancy. Maddie?
As the income increases, the life expectancy.
Yeah, countries that have, on average, higher incomes have a better life expectancy. Well, that makes sense. We all kind of would have guessed that, right? And I think if you go back, you can really see that relationship holds all throughout. There was the Second World War, by the way. I missed that one. See that drop? So this, instead of the data all hovering around the side and the top, now it's spread out more in the middle of the graph, and that's because the scale is logarithmic. But you have to understand that the scale is logarithmic in order to interpret it appropriately. It's not a linear relationship. It just looks linear. Okay, what's this next one? This one's a little bit upsetting maybe, but It's income to child mortality. So death of children under 5 years of age per 1,000 live births. So take a look back in 1802, all the countries that had data were 350 out of 1,000 children would die before the age of 5. Wow. That's a third. That's crazy. Let's see what the scales are linear. You can see it's going up by 50s, 50, 100, 150, 200, 250, 300, 350. And this one's going up by 10,000s. So again, see how they're all huddled to the side? And then you can see it's curved, but it doesn't really give us a nice idea about what's happening. So I think I want to make this one logarithmic. Hold on. And now we're going to see a better relationship and what's happening here. As the income of these countries is increasing, the child mortality rate is coming way down. And in 1955, like this yellow country, what do you think it is? Probably the States again. I wonder where Canada is. If you scroll down and click on Canada, it'll highlight it. And we can track it. And you can even make it like trace out a graph. Which way's faster? This way. There we go. And some of this might be error in data collection. Look at how most of the world, hold on. Most of the world is still huddled way up here. And you're going to find all these green countries that are like African countries that have really low income and really high child mortality rates. And some countries over here that have higher income but still really high child mortality rates. But then all of a sudden the rest of the planet sort of starts catching up. Okay, next, income and CO2 emissions. That one already looks like it's kind of, except all these that are huddled down there. So I guess if we make them both logarithmic, yeah, that's going to show it better. Okay, so let's go back. So again, you can see that it looks linear. It's not linear, but it makes it look that way, and you can just see the relationship in the graph. And what's happening here as the income is increasing of all these countries, CO2 emissions are going up. Who do you think that big white yellow dot is? The biggest emissions producer for, the last century of the planet, basically, the United States, right? Who's that? United Kingdom? Germany? Where's Canada? I bet you Canada's this one. We're right up there. Who's down here? Republic of Congo. Okay, I'm just going to go back. A red dot appears down here, and like watch it fly. There it goes, there it goes, there it goes. It's like a race, and look at it. So that's again China catching up, and they're the world's biggest producer now, I think. There's India, another really big population country. Okay, one more. Try to do it quickly. So this one is this one's interesting. Life expectancy and babies per woman. What would be the relationship for this one? Like, what do you think is going to happen? Daniel?
The life expectancy goes down as the number of babies increase.
Yeah, right? The more babies you have. Why? Is having babies causing them to die? Probably not, although having children is difficult.
Well, the people who usually have more babies are in more impoverished countries.
Yes.
So like they have worse living conditions.
Yeah, so it's a cause. It's caused. They're both kind of caused by something else. Common cause correlation is what we call that. Less educated and less money, and you have more babies, just on average, right? Lots of people have big families when they don't have that. Okay, so let's see what happens for this one. And notice how life expectancy back in 1800 was basically under 40 across the planet, and it looks like average number of babies is between 5 and 7, which seems kind of crazy. And watch what's going to happen. All of the dots are kind of, moving over to the left this time. Usually they've been moving to the right. Babies per woman around the planet is getting smaller over time, and life expectancy of every country is going up, but going up faster in the countries that are moving to the left. And in the last few decades, medical science has really exploded, and so that's what's causing, I would say, as well as just better hygiene, the life expectancy to really skyrocket. And it does, help the entire planet. But okay, so that's it for that. If over the break you want to play around with that, I would encourage you to. It's pretty neat. Gapminder.org. And otherwise, you've got the rest of the period to do the practice.